we didn't make a big to-do about that in our geared turbofan because we called it a geared turbofan. Everyone focuses on the gear. Key technical attributes associated with that. In the case of the turbine, we introduced fuel here. Because of these big fans, another key attribute of this big fan is that the more fan, or the more air we move, the less turbine temperature we need to get that work out of the turbines. What we did, instead of putting higher temperature, what we did is we turned down the cooling flow of how you cool parts. We used our material capability, both in terms of airfoils and coatings, to use that for fuel efficiency. So the cooling levels that we use here relative to a conventional engine today are about 20% less. And we did that in this first generation geared turbofan, really to drive that overall result. So when you look at the 16% fuel efficiency, the key enabler is the gear, but it's every subsystem in the engine that delivers that fuel efficiency. Okay? So what does that mean? As I talked earlier, on the gear, with the gear versus a conventional engine, and you can imagine what engine this is. You know, you call it a direct drive, just happens to be our competitor's architecture. If you then say, well, why does it have fewer parts? It has fewer parts because of the speed that I talked about. We increase speed here, and we increase speed over the whole engine, but because of this gearbox, this speed and this speed is really much higher. So what does that mean in terms of delivery? If you look at just the back end from the turbines, which is high cost, high expense to repair, we have 4 fewer stages, and the stages are kind of designated by lines. There's a disc with an airfoil that's attached to it, or multiple airfoils. Each disc has anywhere from 100 to 150 airfoils that are attached to it. We have 4 less of those stages, 75% fewer airfoils. So when we talk about lower maintenance cost, it's pretty simple. If you don't have the part in the engine, you don't have to repair it. So 75% fewer airfoils. If we go to the front of the engine, 2 less stages, two stages that are different are in the high expensive stages in the high compressor with 10% less airfoils. So the overall characteristic from this is that you have 6 fewer stages and almost 2,000 fewer airfoils in our geared architecture versus the engine that the other company is developing. And I don't care how you price them in a catalog price, if I have 2,000 less parts, it's going to be cheaper to repair fundamentally because of what we've done from an architecture. So that's our real contribution in how we tackled maintenance costs. We also, as I said earlier, we have more air because we make 90% of the thrust or the power of the engine comes from the air that goes out here, not from the air that comes to the center of the engine. So when you have big fans, you actually run the turbines at a lower temperature. What we did is we took the cooling flow out of those parts so we could bring that attribute for fuel efficiency. And that's the mechanism that delivered this key element that delivered the 60%. And then we designed these parts to a much longer time on wing, so that when you look at shop visit or repair interval to repair interval, effectively dropping the overall cost of repair by about 20%. That was our overall objective. So I'm going to talk a bit more about technology toward the end. The reason why I want to kind of bear, everyone talks about, well, why isn't Pratt putting in CMCs? We're the only company that has a 5th generation military fighter. We wanted to put in a CMC. We have that capability. From a cost effectiveness, we didn't need it because we use speed, and we use air, and we use the materials that we have with lower cooling flows to get the efficiency. And then, secondly, you add a lot of product cost. And someone's going to pay for that cost at the end of the day if you're in business. It doesn't come for free. So we really, on our first, I'll say first generation, I'm saying first generation because I'm talking about what we're doing now as we look forward to technology insertion in the years to come. We really try to manage the overall architecture of the engine, what we think to bring the best value. All right. Another key element is on-wing maintenance. if you look at a typical engine like a CFM or a V2500, and you look at what maintenance is required in this engine, we dropped on-wing maintenance characteristics by 50%. So that means there's less to do when an engine is on the wing today with this design than what we've had to do in our base products. And we've done that by putting more capability into the design, less inspections, less interval maintenance, so that we could go from shop visit to shop visit.
So how much are you charging customers for that giant wrench?
We don't. The customers do it themselves.
The giant wrench.
The giant wrench, we provide line maintenance, training. We do very little line maintenance. Want to bring it into our shop, that might be a different story. But if you're really talk about line maintenance, it's teaching the airline or training the airlines to service the equipment themselves. And it's simple. We can take any part off our engine in under 30 minutes. The part can actually come off in 15 minutes or less. So when you talk about an airplane like an A320 that wants to have a 30-minute turn time, we've designed these parts so that if there is a problem with a part, you can replace it within 15 minutes and still make your turn time. So a lot of design went in making sure that we're really bringing the right value to the product. All right. So I want to talk these five platforms individually. We now have 5 customers. We have the C-Series with Bombardier. We have the MRJ with Mitsubishi Aircraft Corporation. We have our recently announced program with Embraer, the E2. We have A320neo, and then we have the Recruit MC21. So I'll talk each one. Certainly, for those who saw yesterday's press release, Embraer has now launched their E2 with 2 significant launch customers, ILFC buying 50 firm and 50 option of their 190, 195. For that model, we will use the PW1900G as the model designation. And as you can imagine, we used the 190 to match their aircraft family. And then SkyWest launched with essentially a 200 aircraft, 100 firm and 100 with purchase rights. And that's on the 175 with our PW1700G. So we take that announcement and we look at the other 4 models of programs that we have, the Airbus, Bombardier, Recruit, and Mitsubishi. We will leave this week's show with over 4,500 engines under order, with over 40 customers. And that's, we're really pleased with the overall market acceptance that we've had with our geared turbofan family. If I look at where we are, to give you an overview of each of our test programs, we now have about 4,800 hours, actually over 4,800 hours of testing on 3 engine models. We've got here the C-Series engine flying on our 747, and then the MRJ engine flying on a modified 747 that we use for experimental testing. And we've now completely certified our C-Series product. On the gearbox itself, we have over 9,000 hours of testing. So we have really spent time in evaluating this gearbox and making sure that it's bulletproof in terms of its service readiness. We've tested this gearbox up to 60,000 feet altitude, simulating 60,000 feet of pressure characteristics in the gearbox with attitudes or angles of attack up to 55 degrees. And a typical airplane maneuver will put this gearbox at about a 2G maneuver load. We've actually tested this gearbox as high as 5 Gs. And we actually did 40,000 takeoffs with 5G loads on the gear train, just to show the overall capability of the gear staying in line. So we're really pleased with the overall durability. So when the competitor says, 4 or 5 years ago, our competitor would say, well, the gear won't work because there'll be hard keeping lubrication. Well, it does stay fully lubricated. It has no life limited parts. And right now, our inspection interval would be every 30,000 flights. We'll start service that way, and then we'll see if we expand that just with adequate service experience. So on our C-Series engine, we certified that engine in February of this year. We have about 3,000 hours on the engine program to date, of which about 335 hours on our 747 altitude test program. We've now delivered power plants for the first 3 CS-100 flight test aircraft, and that first airplane is within days of making its first flight. And then we've done all the detailed work for service readiness as well as first flight readiness. We will maintain this engine just as we would if it was an airline operation. In the case of the 1200G, which is the engine for the 70 to 98 passenger MRJ, we're about halfway through the test program. We've got about 1,600 hours, and we'll initiate certification testing late third quarter of this year. The engine will be certified next year. And we've made sure that we've kept our engine schedule in line with where the airplane program is, where the airplane will go into service in fourth quarter of 2015. Just to put it in perspective, well, have we really tested this engine? Have we really put this engine through its paces? Just to take just the first 2 models, the C-Series engine and the MRJ, to date we have done 6,500 heavy endurance cycles, meaning really bringing the engine to full power, takeoff, and really sitting there and dwelling at that high temperature to look at the integrity of the engine. Of that testing, of those total hours, we have 50 hours that we've run at red line speeds and temperatures, really to make sure that we've put that margin testing in to validate the integrity or the durability of the configuration. And we've certainly, as part of any certification program, we have to do bird ingestion, multiple bird, large geese, fan blade out release. This picture on the right here is the engine, the C-Series engine, after it had released its fan blade as part of a demonstration of maintaining or containing that blade. So we're quite pleased overall with the characteristics of the engine from a durability and maintainability. The 1100G, we've got about 450 hours. We now have 4 engines at test. On the 450 hours completed, we've now did our first flight on May 15th. We've completed 7 flights. We have about 9 to 10 flights remaining on that flight test program, and we're really pleased with the results. The engine is operating better, performance-wise, about 0.5% better than what we had expected, and we're within tenths of our guarantee to Airbus. So we're really pleased with the initial results. And as you'll see from just the cat-dog fight that Pratt & Whitney and General Electric have, we're about a little over 50% of the market capture. So we're really pleased there. And in the case of the high thrust engines for the A321 product line, we're at about 75% of the market capture there. So we're really pleased with the overall market acceptance, especially with the higher power. We've completed cold weather testing. We've got a new test facility. It's about 950 miles north of the U.S.-Canadian border. And we've now taken our 1100G to this facility and completed the icing testing required for certification. As we tool up these 5 models and look at what we're doing for production capability, we've now developed 5 assembly sites. We use our site in Connecticut, which has been there for a while. It's been our base assembly. We've got an assembly site in Nagoya for the MRJ, Nagoya, Japan. We'll do the C-Series engine in Canada, and then we'll also do the Neo engine in Florida, as well as at the MTU facility in Munich. So the whole production readiness and getting that supply chain is well on its way to support the industrial ramp-up. From a technical